MFA would just be flip everything and divide everything by the coefficient associated with MFA. Right? So you can just write it like this. It's EI over L times KL times cosine KL, 1 minus cosine KL. You flip the coefficient and multiply this by the inverse, well, not inverse, subject the first term with a minus 1. So that becomes Q over 2P minus KQ times sine U divided by P and divided by sine KL. So this is the expression of MFA. There's no trick. It just turns around. That's it. Okay. And what other examples I have to talk about? Let's see here. Okay, and the second order, the fourth order, I think I will pass this one here for now, because we already have discussion on the difference between the second order differential equation and the fourth order differential equation. So I think we can spare that part here. But next, I'd like to move on to slope deflection method or slope deflection equations.
So, quick question on the superposition method. If you go back to the last example, even on the slide. So when you simplify the case for both of them, you're applying the axial force P on both cases. So on the left, if you go a couple pages back, or yeah, right here. So force P. So now you're sort of applying force P on both y1x and y2x.
Yes.
Isn't that using P twice? Like how is that not like sort of duplicating in that sense, because you're splitting the moment and the uniform load, but you're not splitting the axial force.
Okay, and the simple answer to that is this. Maybe you can look from this perspective. From the one before, you know that if you have an end moment like this, or if we can make everything easier, so make it in the same direction this way, moment it's easier to show. Suppose to be like this, right? And the deflection will be something like this. Deflection will be something like this. And the reason why you have to consider this P is because the second order effects, right? So that means you have a second order effect somewhere here. That's why the deflection due to existing moments, that's what caused the second moment or the secondary moment effects. Now, if you don't have this force considered, you're not going to find the second moment effects. You'll just be finding just the primary order moment. So that's one reason. Another way to look at this is to understand that in both cases, in this case, if you forget about this P, you have two different loadings. You have Q and you have MFA, right? They will both be amplified by P. Would you agree?
Yeah.
That's why we have to consider P in both cases.
If
you only consider one P in one case, that means you only consider, for example, only one Y1. You only consider the second order moment effect. That means you only consider the amplification for Q, not for MFA and MFB. Is that true?
Yeah, I understand that, but because like, should we just use half, like distribute the P in half for both cases so that we still get the secondary moment, but it's not as amplified as it would be if it was a full axial force P?
No. Why we always consider P, not just half of it? And it's because when you apply the force, they will both introduce a deflection for Q, and for MFA, MFB, they both will introduce that one. And so you can imagine that the portion for Q may be just like this much, and more portion for MFA will be increased a little bit. If you have these initial deflections, and the P will be applied to this initial deflection, which means that the amount of the amplification that will be distributed to Q and distributed to MFA and MFB is all from P, not half P. So you cannot divide it by half. You cannot divide it by half to say that this half of it goes to it, because the implication from the loading axial force on Q in this case is the whole P, not half the P. Okay, if it's still not clear, and maybe after class I can further discuss this with you. All right?
Okay.
Sure. Sorry. So next we will continue this topic, and which is slope deflection. Okay. You can call it slope deflection equations or slope deflection method. So let's start with the example 11. Which we just analyzed this case with a P and also in moments like this. Then we have MA, MB. We have solved this problem. And from here, we found the expression for deflection to be y of x. So this is going to be step 1 equals to, this is the one we did before, but I was going to show you how we're going to arrive to the slope deflection equations in 2 steps. This equals to MA cosine KL plus MB over P sine KL. Of course, this part you already seen it before, right? This is just copying the result that we did from example 11. And this plus MA over P times cosine KX plus MA plus MB over PL times X minus MA over P. Okay. And like what I promised you before, that we're going to separate MA and B. Now, here is the result I will give you. So if you separate MA by taking the MA out, and the coefficient that MA is subjected to will be -1 over P times this whole thing, which is cosine KL over P sine, P take P out, so it has only sine KL. And the other one associated with MA is what? Is cosine KX, right? But because you take the -1, you take the negative sign out, so you have to subject this one with a negative sign. So it has to be minus cosine KX Actually, we forgot the sine kx here, right? So there should be a sine kx. This thing times sine kx and minus cosine kx. And do we have anything with MA? We do. We still have L over P, X over PL, right? And with P is already taken out, so that means this one is just negative minus X over L. Why is it minus
Professor,
sign?
do we take minus MA or we take only MA?
We take only MA.
Okay.
And anything about MA, there's still the last term, right?
What?
We still have the last one. So the last one is minus MA over P, but you already take the minus 1 over P out, so this is just going to be plus 1. So that's everything about MA. Did I miss anything?
Professor, I have a quick question about the drawing itself. Why are the moments going in the same direction? You might have explained that already, but I'm just curious.
Why what?
Why are the moments on the diagram going in the same direction?
That's how we consider the problem from the beginning. Why we have both moments in the same direction is because we want to consider the buckling of a beam column in double curvature, which is possible.
Okay, thank you.
So that's from example 11. That's what we discussed before. Okay. Now this is just the first part because we only have the MA. There's also the other part, the second part, which is MB. Now let's look at the MB part. So part with MB is plus MB times minus 1 over P times this coefficient. It's sine kx over sine KL. So let's check. Come back to here. Sorry, I wish I can put it on the same page. What's MB? MB is this thing, the coefficient associated with MB is sine kx and also sine KL, right? And don't forget there's a negative sign here. So that's the first term. What about the second term? The second term is just this one, x and L. We already take the P out. So that makes the second one just to be minus x over L, right? Do we have anything else? Anything else? Nothing. So that's it. So this, and that's MB. So now we have separated MA and MB in expression of y of x. And we'll do the same for y prime of x. So this is step 1, and for step 2, we're going to write the expression of y prime of x, which is a slope, in the same way. Now, I will just give you the final result because I already explained to you how I got it. Here it's just MA times negative k over P times cosine KL over sine KL times cosine kx plus sine kx minus 1 over KL. So this is MA. For MB is plus MB times negative K over P times this whole thing, which is cosine KX over sine KL minus 1 over KL.